Hello, everyone. Letting some people join. Hi, John. Hi, Abhishek. We'll get started in a couple of minutes here as people are trickling in. Maybe one more minute or so. Hello, George. I see in the chat we have a question about alternative to 4090s for local inference, and best alternative to two 4090s was suggested as four 4090s. Amazing. All right, let's go ahead and get started here. So today we're going to be talking about acceptance testing and validating machine learning hardware. So this is a pretty big topic, but I want to go over, kind of how we build robust clusters, whether for training or inference, and make sure that they're going to run to specification and run at full performance, and how people can really get the most out of their hardware and what we do it together to ensure that that's the case for the clusters that we build. So quick introduction, this is me. My name is Ryan Lucchese. I'm on the engineering team over here at Together. I like distributed systems, AI, high performance computing, open source, and I am working on the Together cloud platform and the hardware automation. So A lot of stuff around how we test hardware is a big part of that. So that's will be the topic of our discussion today. So this is the agenda that I have for today. There's something in that bottom corner, so I'll get rid of my camera for a second so we can see it. But we'll discuss some motivation for why it matters, and kind of the philosophy of how we go about these tests. And then we'll kind of break the test down into 3 big categories of storage, networking, GPUs. That's kind of the fun one everyone wants to talk about. And we'll leave some time for Q&A at the end, so we can do kind of some live questions and answers. If you have questions in the meantime, I'm watching the chat here on the live stream, so feel free to post questions in the chat. I'll try to answer them as I see them come up. Otherwise, then at the end, we'll have time for questions as well. So this is what we'll be talking about today. Motivation. Why does it matter? Why do we test hardware? We could just kind of wait until things break and then deal with it at that time. But we found that not to be the most efficient path. Testing hardware thoroughly is really about preventing problems. Nobody wants to lose training time because of hardware failure. And that's kind of a common thing that occurs, unfortunately. So by testing ahead of time, we can actually detect some impending failures early, and then get those nodes repaired or deal with that ahead of time. Another big thing about that is that when we go to diagnose these issues, they can be pretty subtle. So sometimes, for example, we might see like a loss in performance rather than something just stopping working. And a loss in performance that's a very difficult thing to track down sometimes. It's like, could be storage, could be networking, could be GPUs, could be software, could be hardware. There's a million things that go wrong. And so we want to make sure that we have the fastest path to diagnosing these issues. And a really thorough and structured set of testing is kind of what we found is the most useful way to do that. So one of the key metrics here is, of course, like time to resolution. If we have an issue, how fast can we fix it? And one of the big factors in time to resolution is time to diagnosis. So that's really kind of a lot of the motivation here. We want to make sure that we can detect issues early. We want to make sure that we have the right diagnosis when we do have a problem, and we have that diagnosis quickly. So a little bit about our test philosophy, about how we'll go into the actual testing of the hardware. Many of you may have seen Maslow's hierarchy of needs. This is a GPU systems hierarchy of needs. So, at the bottom, we kind of have some basic needs like drivers and operating system. And then on top of that, we have GPUs and networking. Those are listed here as psychological needs. Obviously, they're not psychological, but that's the format this is usually presented in. And then NCCL, NVIDIA Concurrent Communications Library here at the top. So in a lot of ways, this represents how we build our tests, because we want to fail fast, we want to fail early. There's no point in running really extensive, long-running tests for things that we can know quickly are a problem. So fail fast and fail early is a really important concept in how we design our tests. The tests are hierarchical, so that's kind of related here. That's part of why I chose this diagram for this slide here. There are tests which depend on other tests passing. So nickel being at the top of this pyramid is because when we get to testing nickel, we're testing both the GPUs and the InfiniBand network or the Rocky network or whatever fabric GPUs are communicating over, maybe NVLink. If the GPUs are broken, well, there's no point in testing nickel. So we kind of build up our tests, starting at testing the most basic things that we can test component by component, and build into testing entire systems, and then testing entire clusters. So that's really kind of the hierarchy that we're trying to build up here. One important distinction that we make about tests is that some tests are intrusive and some are passive. This is important because a passive test can be run frequently, not just, earlier we mentioned acceptance testing. Well, acceptance is like, is this hardware, whether it's new hardware, or maybe it's come back from repair, is this hardware ready to go? Is it accepted to be put into production? And passive tests are important as a part of acceptance testing because we fail early, but also as a part of ongoing testing to make sure that hardware is running well over time. It's important to our test philosophy to test every component, to test real environments. So that means the actual driver version and nickel version and CUDA version that we plan to run on this cluster should be tested in that environment, not just in a test environment. And to test real workloads, we'll get into the kind of specifics of what our tests are, but testing real workloads is interesting. One of our final tests is actually training a model on these clusters, and it's one of the most comprehensive tests we have because it proves that a cluster can do what we expect it to. So, but we build up to that through this hierarchy of tests. And an important thing about this as well is to start with a specification. I have this quote here. I think it's a quote. I don't know where it's from. I tried to find it. I can't find where it came from. But everything not measured is broken. I'm usually an optimist, and this is a very pessimistic quote, so it's a bit out of character. But when it comes to testing, it's kind of the right frame of reference, is that everything not measured is broken. So what does it mean to measure something? Well, it means we have to have some specification to measure it against. And that can differ depending on the systems that we're testing. Like nickel bandwidth is going to be different on different configurations of networking and so on. So we should have a specification. We should have a measuring stick by which we're going to measure each of these things. And that's really core to the whole testing philosophy here. All right, let's get into some details. So we'll start with storage. Storage is really one of the main kind of components here, storage, networking, and GPUs when it comes to these AI, ML hardware. Those are really the three most important things. And so here's a useful abstraction in how we can think about storage as some kind of 2x2 matrix of storage tiers. So, and this is an oversimplification. It's just useful for how we think about storage. But there's slow storage and there's fast storage, and there's local storage and there's shared storage. And those are two interesting dimensions to break down storage because we often find that it's desirable to have multiple categories of storage. And how we build our clusters is that, kind of the gold standard is, of course, fast shared storage. It's easy to access on multiple nodes because it's shared, and it's very high performance. Um, the next sort of most interesting form of storage is probably fast local storage. This usually takes the form of like NVMe drives on the GPU systems. Especially with like a large number of drives in RAID 0 or something, this can be very fast, but it's local to that system. So it's hard to share data between different systems. And then on the slow storage side, I think, we're generally less interested in slow storage, but slow shared storage is sometimes interesting. And that usually takes the form of NFS, not as a protocol, but some sort of NFS mount that's shared from maybe the head node is sharing NFS to GPU nodes in some configurations. And really the point of this is to share scripts, to share log files, things that are really not performance critical, but configuration files is another good use case of this. Things that are not performance critical, but we do want to share across the nodes. So this is in some way starting with a spec. So we're kind of breaking down our storage categories here, and then let's go test them. So benchmarking storage. What are we measuring? Oh, there's so many things to measure with storage. We've got latency, bandwidth, IO operations per second. Each of those we do sequential versus random, and then we do read versus write. So there's a lot of numbers when it comes to storage. But the good news is there's generally just kind of one tool that does it all, and it's FIO. So what are we measuring? All this stuff. How are we measuring it? FIO. Over here on the right is some FIO output. This is, a little bit of a mess of shell output here, just kind of pasted onto this slide. But the reason I decided to share this output is because it shows kind of how extensive FIO really is. This is really just one job. This is a sequential write job in FIO. And we can see here I know the font is tiny, but if you look in about the middle, there's a bandwidth measurement, there's an IO operations per second measurement, there's a latency measurement, there's a measurement of CPU usage. So really, as many parameters as storage has, we've got a pretty great tool for testing them. So when we run FIO, we generally like to run it containerized. And the reason is because it just allows us to ship jobs easily around, as well as, the file binary itself. So we organize FIO into all of these different jobs based on all these things that we have to measure, like the latency and the bandwidth and IOPS and sequential read and sequential write and random read and random write. And we organize FIO into all of these jobs. We put all of that into a container, and we're able to just kind of quickly go collect all of the stats using this FIO container in these jobs. So FIO is pretty cool for that. It's, measuring a lot of things, but easily in one tool. Particularly when it comes to the fast shared storage, another advantage of running this containerized is that we'll probably want to run multiple jobs at the same time. Oh, we have a question. Question is, since it's a cluster, shared storage will be used. Which is better, VAST or Weka? How's the performance comparison, NFS versus fast shared storage? So which is better, VAST or Weka? I really like them both a lot. They're amazing systems. They're both can perform extremely well. There's a little bit of differences in the ways that they scale. Weka tends to kind of scale almost linearly with the size of the storage cluster. And VAST you can scale data and performance independently in VAST. So their scaling characteristics differ a little bit. When it comes to using VAST or Weka on an AI training cluster, we've found great success with either of them. They both work very well. They both meet our performance needs. I can't say that either one is better, honestly. I like them both so much. And as for the performance comparison between NFS versus fast shared storage, that's pretty significant. So, and by pretty significant, I mean very significant. Excuse me, choked on pepper. So when we set up NFS, I mentioned before, it's like for sharing scripts usually is kind of the intent. If we start hitting NFS with performance critical workloads, it doesn't hold up to the stress the way that something like a VAST or a Weka would. It can, in severe cases, bring down the node that's serving the NFS export. And in terms of like, if you were trying to put training data on an NFS drive or write checkpoints to an NFS drive, the result of that is generally that your whole training performance would be reduced. So your storage is just not fast enough in that case to keep up with the GPUs and the high-speed networking. So that's really kind of the crux of why we recommend VAST and Weka is we want to keep the GPUs going at full performance at all times. And VAST or Weka are a great way of doing that. NFS is really not. Alrighty. Thank you for the question, Abhishek. Let's talk some networking stuff. I ordered this presentation in between storage, networking, and GPUs. I ordered it in my favorite order. So I think it's like increasing interestingness. Networking is where things get a little bit more interesting, in my opinion. It's just how I feel about it. Skipping ahead. So generally our clusters will come with two forms of high-speed networking. We usually have an Ethernet fabric and something of a compute fabric. Or sometimes we call the Ethernet fabric or the in-band fabric or the management fabric. And then the compute fabric is either InfiniBand or it could be Ethernet as well, usually Rocky, RDMA over converged Ethernet. So we'll start with Ethernet. We'll go to InfiniBand next. Rocky is similar to InfiniBand. We don't really need to get into the distinction here, but so when we go to test Ethernet, the main tool that we use is iPerf3, and there are some other tools, but iPerf3 is pretty good for most the type of test that we want to run. So the way iPerf3 works is you launch both a client and a server. So this test will take two nodes if we want to test, kind of the in-band fabric between two nodes. We can run it on more if we need to also. But we'll run a client or a server on one node. We'll run a client on another node that connects to that server. And iPerf does some data transfer over the network, and then it measures the throughput essentially. It's a great tool for this because there's a lot of parameters in how you run iPerf. So one of the things that we found, and this in some cases affects people doing online training or usually these in-band fabrics tend to be in a lot of use cases less used than the compute fabric. But there are cases where these fabrics are stressed pretty extensively. So one of the things that we found is that data transfer can be bottlenecked by CPU fairly easily. So iPerf is a great way to show and to kind of discover the parameters of that. So we can run iPerf with different concurrency values with this minus P parameter, minus capital P. And this is on the client side, and it basically says, don't just run one iPerf against the server, run 16 of them or something. And if you want to get close to the line rate of a high-speed Ethernet, like 100 gigabit Ethernet, 200 gigabit Ethernet, if you want to get close to the line rate of high-speed Ethernet, you have to use concurrency because your single thread is not going to be able to push enough data. But you can try this with different parameters and kind of sweep from, like one thread all the way up to 32 threads, however many, and you can kind of figure out exactly what that relationship is. So this is the thing that's really great about iPerf. The window size as well is important. We'll talk about this in an InfiniBand context as well, but how much data you're transferring is, of course, going to affect the bandwidth at which it transfers. And when you get to really small amounts of data, there's so much, there's so much overhead around kind of like establishing that connection that the bandwidth is going to be lower on kind of small message sizes. So iPerf is really the main tool for Ethernet testing. We run it in a bunch of different modes, kind of like FIO. It's pretty flexible. And it's useful for proving that things can run at line rate, but also that discovering sort of the parameters of what's needed to get fast data transfer on this fabric. InfiniBand. So InfiniBand is generally going to be our compute fabric on most of our clusters. We have some Rocky clusters as well. But for InfiniBand, we have a pair of tools that we use to test, which are IB write BW and IB write latency, lat, IB write lat. So this is for measuring bandwidth and latency. These tools are pretty cool. They're really, I think, less comprehensive than iPerf in the sense of they're kind of a little bit more focused towards doing one or two things and doing those things well. But IB write BW is one of the kind of really important tests for us as we're going through, say we get some new hardware in and we're going through all of the tests in our and we want to see, is everything working? Well, IB write BW is a point where kind of the first time you run it on a cluster, you hold your breath a little bit. Not because you expect it to go wrong, but because you can get a lot of information because there's a ton of links on one of these clusters. For a training cluster with 1,000 GPUs, we have 8 InfiniBand connections per server, or 1,000 GPUs with 1,000 InfiniBand connections. So there's a lot that could go wrong with these connections. There's just there's a lot of them, and that's 1,000 InfiniBand connections. That's just the connections from GPU to the nearest leaf switch. There's also connections from the leaf switches to the spine switches. So measuring this at scale is really is an interesting point in the testing process, I guess, because it could be anything like maybe there's an optic that's dirty, there's a little bit of dust got in the fiber optics or something. This would show up here. So what we do when we run these tests for InfiniBand is we try to light up the entire compute fabric at once. And maybe that's why it's part of a hold your breath kind of moment as well, is because it's one of the first whole cluster operations that we do with new hardware. But we try to light up the entire fabric at once. And what IB Write BW does is just like iPerf in the sense that you start a server and you start a client, and it does some data transfer between the server and the client. It measures the bandwidth. IB Write latency is the same thing, except small message sizes, more concerned about latency. So when we light up this whole fabric at once, we're kind of stress testing a few things. We're stress testing the transceivers, the optics, the switches, the HCAs. There's a lot of components that are now kind of all being used simultaneously. And what we do when we run this test is we light up all of these InfiniBand links, have them transferring data, and we just watch to see if there's any errors. So this is partially a bandwidth test and partially a stress test. Transferring that much data is going to stress the switches out a little bit, especially because they're having to switch large amounts of data at a very high speed. And what we'll see is if there is something wrong here, we'll see error counters go up. And so this is one of those cases where the problem, there might be a real problem, but it can be very subtle. So imagining like a dirty optic or something, there's a little bit of dust in a fiber optic cable. And what we might find is that we light up all of these links and we find that there's kind of an error counter on a certain one, maybe like some kind of packet retransmits or something. We see error counters go up because the link is working, but it's not working at 100%. So in that case, like usually if it's a dirty optic, the remedy is very easy. You just clean the optics. But in that case, these sorts of things, if you don't have comprehensive testing like this, can be very difficult to track down because you're just dealing with, okay, well, there's a performance issue. And going backwards from there's a performance issue, you don't even know if it's networking or GPUs or software or hardware or what. Can take a long time. So that's why it's really important to like have this sort of systemic way of diagnosing these issues and testing all of these things. But yeah, that's how we test InfiniBand. We light the whole cluster up. We let it run for a while at this high throughput mode, stress test all of these parts, and watch these error counters. These error counters, by the way, are a great example of a passive test. Earlier I mentioned passive tests. And the error counters are something that can be observed all the time. So we have observability systems on our side that monitor this. And if we see things change, even during running production workloads, not during a test, we can watch these error counters. So these are a great passive test as well, by the way. All right, the part everyone probably actually wants to talk about, and my favorite part, the GPUs. One of the first tools we use for testing GPUs is a tool supplied by NVIDIA called DCGMI. Probably many people are already be familiar with this tool. It's one of the things that is kind of a standard tool when it comes to testing GPUs. It does a lot of things. So there's kind of a bit of a rabbit hole you can go down in reading about all the things that this tool can do. It's a very, very comprehensive tool. But the main one that we use really is DCGMI Diag. So Diag is diagnostics. It has a fail early, which makes me happy for our testing philosophy. Was literally on our testing philosophy, so fail early is great that it has this. But there's a run mode that's specified as 1 through 4. And so this run mode can do both passive and intrusive. So DC-GMI diag in run mode 1 is very quick. It finishes in seconds, and it doesn't interrupt any workloads that are happening on the cluster. So this is great for observability. It's great for detecting problems that that can be detected without needing access to the GPUs directly. And it goes all the way up to R4. R4 is like I forget exactly how long it takes, but I want to say it's like 90 minutes. It's a pretty comprehensive test, R4 is. And R4 does everything from stressing GPUs out, trying to measure if they do any thermal throttling, trying to measure if they can reach their maximum power output, doing checks on the memory to see if there's, when they do certain memory operations, if there's any errors in those operations. So R4 is a very comprehensive test of the GPUs themselves. So when we're doing acceptance testing, R4 is usually our go-to here. We'll just kind of run, and thankfully it's got fail early, so if something's wrong, we don't have to wait 90 minutes to find out that something is wrong. But we run R4 when we get new hardware or when hardware is kind of being reallocated to a different purpose. And that gives us pretty good sense of whether GPUs are actually working. GPU burn. This is the coolest slide in this deck, so it's all downhill from here. I made this image with a together endpoint, by the way. This is the Flux model running together. It did a great job. It has for a GPU on fire. But GPU burn doesn't actually mean that we light the GPUs on fire usually. A GPU burn is a tool that is meant for stress testing GPUs. And the nice thing about GPU burn is that we can run it for a longer time frame. So, this could be 2 hours, this could be 12 hours, or longer in some cases. The reason that this is important, because DC-GMI, and thinking back to our test philosophy about how we build up this hierarchy of tests, DC-GMI will have already stress tested the GPUs individually. And in many cases, DC-GMI will catch issues before a longer-term GPU burn would. So that's why we run it first. But GPU burn is still a very important tool in our toolkit because it allows us to put these GPUs under stress for a period of time. And that does a couple of things. That will expose any issues with thermal throttling. So this is also one of the things DC-GM tests, but it tests it for a short period of time. But testing it for a longer period of time, we can find thermal throttling issues. And we also really like to run this cluster-wide. I'll tell kind of a funny story. I visited a data center one time, and the people that were working in the data center were taking me back to the cage, and they were like, they basically said, it's going to be quiet in there because you're here with us. But when you're back doing your things together, we can tell as soon as you get on the cluster because the whole data center gets really loud all of a sudden. And I have a feeling they were talking about GPU burn when they said that. Because this will generate a lot of, it'll use a lot of power, it'll generate a lot of fan noise, and it will get the GPUs hot. So that's what we want it to do. And we want it to do that at a rack level because DC-GMI will probably do this. It does it at a machine level. But if all the machines aren't running the stress test at exactly the same time and so on, it's hard to heat up a whole rack with DC-GMI. But with GPU burn, we can easily heat up a whole rack. So if there are any issues with power or cooling at a rack or data center level, this is going to really kind of bring that to light. So that's part of why we like it. Usually most things are caught by DCGMI, but this is a still quite important tool. And my favorite thing about it is that the GPUs usually don't actually catch on fire. Usually. All right, NV bandwidth. So I actually debated putting this slide in the networking section because this is a communication technology, NVLink, NVSwitch as a communication technology, but it's also GPU specific. So here it is in the GPU section. This tool is pretty well analogous to something like IV Write VW. What it does is it copies memory between GPUs on a system over the NVLink fabric that's on that system. This is a pretty useful tool to make sure everything's performing well with NVLink and NVSwitch. And this is another one of those things where an NVLink is made of a bunch of lanes, and you can end up in some degraded situations where performance is affected, but the fabric is still functioning. So NV bandwidth really gives us confidence that an NVLink fabric is functioning at full performance. But we're really looking forward to using this more on the GB200 systems because there's been such an expansion of NVLink with these GB200 systems. We've gone from 8 GPUs in an NVIDIA NVLink domain to 72 GPUs in an NVLink domain. So a lot more traffic will be moving over this particular fabric in the GB200s. So I think this tool will be even more relevant in the future than it is today. Nickel tests. This is a fun one. This is the other point where in a cluster build that we kind of hold our breath, because we're building up. We've tested kind of component by component, and we're building up to starting to test a lot of stuff at once. The nickel test both the GPU and the InfiniBand fabric. We generally all-reduce perf. So we're measuring performance of the all-reduce operation, the nickel test here. Nickel tests are not quite a real workload, but this is starting to get close to a real workload because all-reduce is one of the key operations. And oh, you can all hear the cat. Yeah, his name's Hank. He's very needy. I'm not sure why he's at my door meowing, but I'm sure if I let him in, he would probably climb all over my laptop. So yeah, back to nickel tests. So for all reduce, it's one of the key operations in training a foundation model. So it's really something that's interesting to us to measure performance on. And this test, when we run it, we start with a single node. We run on all of the nodes as a single node, because we want to know, can the GPUs on a single node communicate between each other? And then we start to build up, because we're going to start with, can the GPUs on a single node communicate between each other? And we will move all the way to, can the GPUs across the whole cluster communicate to each other? Abhishek asks, do we run the nickel test via MPI? Yes, generally. So in a single node nickel test case, no, because we don't need MPI for a single node. But for multiple node nickel test, we generally run this with MPI. That can take a lot of different forms as well. So we do both Slurm and Kubernetes clusters. In the Kubernetes side of things, the MPI operator is really great. It's a great way to run these. Can easily kind of schedule them on the nodes that you care about, and easy to automate and all that cool stuff. And then on the Slurm side of things, just kind of srun, MPI run, kind of standard Slurm stuff. But yes, we do use this with MPI. This is one of the things that can make a pretty significant difference as well. We've seen, and this, is more on the software side of things. There's a million combinations of software that we can use to get a training job running, and the choice of kind of which MPI makes a difference, we've found. So we've had really good luck with HPCX. That's generally kind of the one that I would recommend, is using HPCX. But yeah, this is definitely a hold our breath moment in the cluster, because if something is going to go wrong during the acceptance testing phase of a bunch of new hardware, this is probably where we'll see it, unfortunately. The reason I say unfortunately is because this is, by the time we get to nickel test, we're testing enough components together that any one thing going wrong, kind of our odds of failure are getting higher and higher the more things that we're testing at once. And any one thing going wrong can bring these nickel tests down. So, and this is a notorious one for performance is reduced, but it still works. We kind of joke internally that nickel finds a way. Avishek has another question. Which one would you prefer, Kubernetes versus Slurm? Personally, I really like them both. I like Kubernetes more for inference, and I like Slurm more for training. So there are people who train on Kubernetes. I don't know of anyone doing inference with Slurm, but there are people who train on Kubernetes, and that works pretty well. There's, I think, increasingly a trend in that direction. But Slurm is great too. And then there's also Slurm on Kubernetes is something that a lot of people are looking at as well. I know SchedGMD has done they have a system called Slinky for Slurm on Kubernetes, a set of operators to run Slurm on Kubernetes. There's some other implementations of it as well. So it doesn't have to necessarily be one or the other. It can be both, but they're both good for their own things. Slurm is very much more kind of simple system. It's easy to experiment with and get going quickly, and it's very efficient for running training jobs. Kubernetes is a little bit, I think, better for kind of production workloads, maybe serving traffic over the internet, that sort of thing. But yeah, generally when we run nickel tests, the thing that we're looking for is that we can get pretty close to the line rate for the compute fabric. So in a lot of ways, we're kind of looking to get almost the same number that we got from IB rate BW. But that's a good thing, because now it means that we're doing compute calculations and we're not bottlenecked by the network. We're able to actually move that all in time. This is a pretty cool chart. It's actually not super relevant to acceptance testing, but I wanted to include it just because I think it kind of helps understand the nickel tests themselves a little bit better. So what this chart is showing, the horizontal axis is on a logarithmic scale. So the actual look of this chart would show a much steeper rise in on the left side of the chart. But in the vertical axis is the bandwidth. So transfer rate, throughput rate. And we can see some interesting things from this chart. I guess the immediate takeaway is that the general trend is kind of up and to the right, which means that a larger message size is going to achieve a higher bandwidth. And that's fully expected. It's kind of interesting to note that there are some jumps in this chart. So each of these message sizes, you can see kind of the next message size up will increase, and then we hit a point where there's like a small decrease, and then it increases, a small decrease. So we can see that there's some efficiency considerations to be had around message size. But usually what we're looking for when we run nickel tests is that we can get into the top right corner of this chart. So that's kind of the testing side of it, but this is a pretty neat chart in general I wanted to share. Configuration. Oh, this is one of the most important things about nickel. So before I said if we're going to see something go wrong, we often see it at the nickel test phase. And a lot of the time that we see it at the nickel test phase, it's because of configuration issues. So there's a million ways to configure nickel. You have to make sure you're using the right fabric for coordinating the workloads with MPI. You have to make sure you're using the right fabric for the compute. There's a bunch of settings. So this is kind of almost an exercise in tuning to some degree, make sure that things are running well in a cluster. But one important call out on this slide is that we test with nickel algo is ring. Oh, we have a question about a lot of acceptance testing is about throughput or performance. What about correctness? What sort of tests and what sort of correctness issues do you encounter in these clusters? Yeah, this is a great question. So I haven't talked a lot about correctness, but we implicitly get a lot of correctness through ECC, which is awesome. So ECC is error correcting code. We have ECC memory on both the GPU and usually on the system itself. So there's a bit of a correctness check in that in its own right. And the nickel test is an interesting one for that regard as well, because we're actually doing calculation. So I think as far as correctness goes, when we run nickel tests, we're doing this all reduce operation on GPU. We're transferring data between GPUs. I'm not sure off the top of my head if the nickel test actually checks that the final output is correct. But along the way, the GPUs we do see generate ECC errors if there's a problem with the GPU. And those ECC errors are something that we're looking for to determine, is the GPU doing what we expect it to do? If there is an ECC error, that they fall into categories of correctable or uncorrectable. And a correctable, in either case, if there's an ECC error, it generally means that there's a section of bad memory on the GPU. The GPU comes with some extra memory that can be mapped in, so we can turn off that bad row of memory and turn on a good row of memory. But yes, there's a little bit more discussion about correctness. What do you mean by correctness? At the stack, you're putting output LLM. Anything that can influence numerical correctness per GPU or distributed calculations. Yeah. So really, ECC is a big shield when it comes to correctness. So if we don't have any ECC errors, I think we have a reasonable assurance that we have correct computation of the GPU. If we do have ECC errors, that assurance is not necessarily there. So that's kind of a big aspect of everything. And it's one of the ECC errors are one of the things that can be passively tested, and one of the things that we monitor. So, and it's also a thing that one of the things I mentioned earlier in this presentation was that some tests can tell us whether hardware has an impending failure. And ECC errors are one example of that. So we see if a GPU is about to fail, we'll often see that the rate at which it's encountering ECC errors increases. There's a threshold for how many ECC errors a GPU can have before NVIDIA considers it eligible for replacement. And we've seen before, like GPUs under that threshold will kind of, maybe they get one ECC error at first, and then there's this accelerating rate of ECC errors that they get as they progress towards failure. So that's one of the things that we can use to detect that the GPU is about to go bad. And yeah, someone in the chat also mentioned that NVIDIA Field Diagnostics, that is a pretty good tool that runs comprehensive tests. We generally don't use it for the reason that we like to test real environments. The NVIDIA Field Diagnostics will unload the production grade NVIDIA driver and load in a diagnostic driver. And that diagnostic driver is, of course, no longer your real environment. Not that it's a bad tool, but kind of our testing philosophy here is built around testing these as close to how they will actually run in production as possible. And field diagnostics is, great for kind of running really comprehensive tests, checking correctness. But yeah, it also requires it's pretty intrusive because it unloads your driver. But anyways, it is a great tool. We have a question: do we have success on getting RMAs without running field diagnostics? The answer to that question is complicated. It depends a lot on the OEM. So there are some OEMs out there that will require a field diagnostics, and that's understandable. It kind of gives them something that they can log, and gives them a thorough report of exactly what went wrong. It's not always the case, but I would say more often than not, that is the case, that you have to at some point run field diagnostics. So usually for us, because we have some comprehensive testing in our production workflows, that saves us time, even if we still have to run the field diagnostics for RMA reasons, because we can take the node out of production. We know what's wrong with it. We know it's not software. We know it's memory. We know what field diagnostics is going to tell us when it runs. So it's just kind of a matter of collecting logs at that point. So we can just run it, collect logs, and send them off. So it still saves us time, even if we have to run those. But I think it's something that it's not part of our regular testing because of the reasons mentioned. And that's a really great segue into this slide of like what to do when things go wrong. I know we're almost at time, so just really quickly, I'll mention to do when things go wrong is figure it out. We isolate bad nodes, diagnose it, get it fixed. If anyone wants to follow up on anything else mentioned here, there's a really great article called A Practitioner's Guide to Testing and Running GPU Clusters for Training Generative AI Models by myself and some of my esteemed colleagues. This blog post has commands, expected output, has a ton of detail. So it's a great way to follow up on things discussed here. And with that, we'll see if there's any questions. To give people a chance to type questions into the chat if they want to, or oh, we have a question. Do you use any DCIM? Maybe I'm not remembering, but what is DCIM? Data center infrastructure management software. Um, Generally speaking, cool. Yeah. So there's a lot of context here that's going in the chat. So um, data center infrastructure management software like NetBox, supposed to manage physical source of truth for rack hardware, IPAM. We have a question if the cat's okay. I think so. Um, I'll bring him on the live stream. We'll find out. But as for the data center management software, we excuse me, we actually write our own for the most part. So um, we've tried out a few different things, and for various reasons have decided that kind of the automation, testing, and source of truth and infrastructure management stuff is something that we wanted to build in-house to kind of meet our requirements. A lot of that enables our Together cloud platforms. So these are things that um, make it convenient for our customers to get these well-tested clusters, for us to spin up new inference clusters. Um, so our cloud platform is kind of something that forms the infrastructure layer for most of what we're doing it together. So that's why we went custom. Is the cat okay? I'll bet you he's still outside the door. I'll check. Hey. Not still outside the door, but the door is cracked, so he may come in here in a second. Either that or he gave up and went to go take a nap. We have a question about, is there any automation on the tools and processes that you showed us, and how are the results parsed? Yes, the answer to that question is definitely. So we have automation around this stuff at a few different sort of levels, depending on exactly what we're trying to do. For example, one of the biggest things that can differ is the whole intrusive versus passive thing. Sometimes we're attempting to run really comprehensive tests cluster wide. Sometimes we're attempting to test individual nodes or smaller groups of nodes um, as they go through their life cycle of repair and so on. And sometimes we're just continuously, sometimes all the time, we're continuously monitoring the hardware. So there's a bit of different kind of use cases where some of these tools fall into different things. So they're automated in different ways. So how are the results parsed? In the case of a lot of the passive tests, this is like just metrics. Like DCGMI can export metrics. We can load into Prometheus and run alerting on. We can get a bunch of passive stuff through DCGMI that way. And then the other things that are more intrusive, DCGM has a JSON mode, which is great because it's super easy to parse. Nickel tests are a little bit harder to parse, but they're just ultimately a text file. It's kind of like separated by spaces. So some custom parsers for results have to happen here and there, as tools have different output formats. But yeah, it's not too bad on the parsing side of things. But automation is extremely important around all this stuff. It's like doing this by hand at scale would be impossible. That was a great question. Thank you. All right. Well, we will wrap up, I suppose, if there are no more questions. Thank you all so much for joining. It was great having you here and talking about all this stuff. Really, I hope it is helpful, and there was some good learnings, but certainly from my side, great to talk to you all. Bye.